All right. Yeah, let's get started. So I guess today is the lecture number, 12. And let me briefly recap what we've discussed last time, last week. So we started with discussing the quantum communications. We discussed this no cloning theorem that we will use this theorem today. And we also discussed the concept of shared randomness and how this shared randomness allows us the quantum teleportation effect when the measurement of a qubit or one of two qubits in the state of quantum entanglement affects the state of the another qubit, which can be like far away from the first one. Quantum teleportation. We discussed this. I guess the most popular protocol for the quantum teleportation, when Alice and Bob share two entangled qubits, and then if, for example, Alice wants to send or teleport this arbitrary quantum state of a qubit, she simply measures her part of the entangled qubit in the plus minus basis, and as a result, Bob gets either the state itself or the state with the wrong phase, and what he just need to do, just fix the phase to get the right quantum state. And then we start discussing the concept of a photon as a qubit with application for this quantum communications. We discussed how we encode the quantum state of a qubit into the polarization of a photon. We discussed these three different bases. The rectangle one, this cross one, and the circular polarization. We also say that the polarization state of a photon, well, it's very like feasible degree of freedom to work with, at least at the single photon, at the single qubit level. And that's why this technology like is very developed today. And one particular example is this quantum cryptography, which is I guess the most developed area in quantum technologies today, much more like much well developed than quantum computing. Yeah, and we stopped a discussion of like motivation beyond this cryptography. Why basically we discussed how the classical cryptography works, especially the one based on the prime factor and I mean in general computational complexity, and why we need quantum cryptography. So today we will discuss the quantum cryptography in more detail, and consider one particular protocol for the quantum cryptography, the very first one developed, and at the same time one of the easiest to grasp. So the topic of today's lecture is quantum key distribution. Quantum key distribution. And the protocol BB84. So the letters B and B, just the first letters in the names of the scientists or engineers who developed this protocol, and the 84 is the number of the year when this protocol was first developed. So 84, it was, well, 40 years ago, right? So as I said, this quantum technology is very well developed today. So in this protocol of key distribution, we encode the information in the polarization state of a photon. And just to remind you that, for example, we can consider two different bases for the polarization states of a photon. The first one we consider is this plus state, and the second one is this cross state. Right, and in this basis, for example, the digit 0 would be encoded as a vertical polarization state of a photon, and 1 would be encoded as a horizontal state of a photon. And in the second basis, the 0 would be encoded into this right, well, inclined polarization state, and let me call this left polarization state of a photon. So again, this is just like a photon, and what's difference between these bases and 0 and 1s is just the orientation of polarization of a photon. And this polarization can be like prepared or selected using a number of optical elements called polarizers, etc. And for example, what if we have a vertically polarized photon, right? So like if I have a polarizer with like vertically oriented polarizer, so this is my polarizer, and I make my photon to pass this through this polarizer, what I will get in result of this measurement, right, would be like full transmission of the photon as would no polarizer there. So and if I put a detector right after the polarizer, I will detect, well, it would be I will detect a photon, and for this orientation of the polarization, it would be 0. Right, so I detect the 0 photon. But what if my photon is polarized in this way, the horizontally polarized, and I set my polarizer direction. So, well, I would get no photons coming through. Right. So my detector wouldn't detect any photons that pass through the polarizer. But what if I prepare my photon in this another basis, in this cross basis? For example, a photon like this. And again, I set my polarizer in this direction, and I also have this detector. So what would happen in this case? So in this case, since my photon is polarized like 45 degree, according to the polarization axis, in average, like this photon has a probability of passing through towards the detector of 1/2, right? 1/2 is the passing probability, and the same probability of being reflected or scattered somewhere. So I detect, and if this photon passes through, the output photon, the photon that passes through this polarizer, would be vertically oriented, but it will be just the half of them that go through the polarizer. And similarly for this orthogonal cross photon, it would be again just a half of them probability. It will be just a half of them that go through the polarizer, and those photons that pass through the polarizer, they will be vertically oriented. So this is how the measurement of a photon in one basis works in other basis. If I detect a photon in one basis being in the same basis, I would either detect the photon or don't detect it. So no photon. Yeah, the photon is there or not. But if I measure the photon in another basis being in the first one, I would get the probability of one or another realization. And this is exactly what this BB84 protocol uses for the quantum cryptography. So in this scenario, let me bring Alice and Bob right to the discussion. So I have Alice and we have Bob. Let's suppose we have the security key, right? That Alice wants to share with Bob. So this key would be something like really a random string of digits, of bits, 1 0, for example, 1 1 0 1 0 1, something like this. A randomly generated number. So, and for example, if Alice and Bob share this random key, right, then we can go back to the previous lecture and see how they can. Where was that? Yeah, here. So suppose they have this random key, and they share this secret secret random key. Then they can encode any information using this key, and Bob can get the information in a secret way or protected way. Right? So Alice wants to share this random key with Bob, and and they have two channels of connection. So the first one would be classic. This classic, like a phone or whatever. This classical channel of communication. And another one is this, let's call this quantum. In fact, it's just optical fiber that allows propagation the photons through the fiber. And this fiber is, it doesn't affect the photons much. So they preserve the polarization state, the frequency, and all the parameters of the photon are preserved. All the parameters of the photon preserved. So first, what Alice does, Alice generates the, she randomly chooses the basis. The basis sequence. The basis sequence. What it means. So let me change the color, for example, to this one. So basis of Alice. So basically she has two options, either this plus like or cross like basis, right? For example, and this is really a random process, so it can be plus here, something like this, plus plus, cross cross cross, for example, something like this. And according to this basis, she encodes the information, these digits, into this into the polarization of a photon in the each particular basis state. So for example, let's call this photons. Photons. So we see, for example, the first digit 1 in the plus basis is the horizontal photon. Write it like this. So it will be a horizontally polarized photon, like this. So the second one will be the polarization like this. Then one in this cross polarization would be like this. Then this is horizontal, then vertical, then photon like this, and finally polarized like this. So this is the information encoded into the randomly selected basis states, and Alice sends these photons with these polarizations to Bob. Alice sends the photons with encoded information or key information to Bob. Right. So what happens next? And the communication between Alice and Bob are synchronized, and when Alice sends these photons to Bob, Bob receives the photons and he measures the photons in a basis. And again, what he does, he chooses the basis randomly, basis of Bob. And yeah, so this is again the random process. And for example, would be something like cross, cross, then plus, plus, cross, 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 plus, something like this. So just to emphasize this point, so this key is random, right? So it's generated by random generator. Then this basis of Alice is also random, and basis of Bob is also random. Also random. And let's write this down here. So Bob measures the photons in the basis sequence, in the basis sequence. The basis sequence he randomly chooses. And what happens? So again, as we just discussed, for example, if he receives the photon that is, for example, horizontally polarized from Alice, and for example, Bob selects this cross polarized basis to measure the photon, what he would get? He would get 1/2 probability for getting this right photon, right, and 1/2 probability to get the opposite polarization. And let's return to this table and check what he would get. So, I mean, after the measurement, Bob will get the bits, right? So, bits of Bob. Alice, well, the key is the string of bits, and Bob measures the bits, but the information between Alice and Bob is encoded into the state of a qubit. So let's, for example, consider this first column here. right? So the photon that Alice sent is horizontally polarized, but Bob chooses the cross basis to measure it, and he can and he can get either this or that result, right, of the measurement with the equal probability. And so let's suppose he gets, for example, 1 in this basis. But the basis he chosen was different. Another one comparing to the basis that Alice used to send this particular bit. So the next one, he chooses the right basis, and in this basis, this photon corresponds to 0, right? So it will be 0. Then again, this is wrong. Let's say he gets 0, then this also, let me see. So then, so this one is horizontal is 1. So this is okay. Then again, we have the wrong basis. So let's suppose he gets 1. Then we have right basis, so it's 1. Then the right basis is 0. And finally, the basis is wrong, and let's suppose he gets 0. So let's denote the correct and the incorrect basis. So the first one was incorrect. Then the second one was correct. Let's choose the incorrect one. So this one is also incorrect. Then this one is incorrect, and this one is also incorrect. And the correct bases are this one, and this two. Very good. So what happens next? So Bob measures the polarizations of the photons that he receives from Alice in a basis that he randomly chooses. But for now, he doesn't know which, what basis Alice chosen. And when he measures the photons, Alice can send, I mean, basically they communicate, Alice and Bob, they communicate over the classical channel. And Alice tells Bob, or better to say, Alice and Bob, they compare the basis sequence, compare the basis sequence. And they remove the they remove the bits that don't coincide. So in our particular case, they would discard the, for example, this one, this one, this one, and this one, right? And only keep this correct bits for key distribution. And after that, so this way they Alice sent the correct bits to Bob, and they can use these correct bits for as a key for cryptography protocols. And roughly 50% of the bits are wrong, right? Bob choosing the wrong basis to measure them, and these bits are not useless. They can also share this sequence of these wrong bits, and Alice can do some statistical analysis to check if there is a eavesdropper, right? The person who tries to get eavesdrop the communication channel. Yeah, so this is pretty much how this protocol works. So it's pretty easy to understand, and this is the easiest protocol for quantum cryptography. Now what else? Let's discuss what happens if we have a eavesdropper in the system. Right, this is important. So, so if you have a eavesdropper in the system, this is called, I mean, this type of attack to the security of the communication channel is called MITM, right? So it's called MITM, which stands for man in the middle. Man in the middle attack. Man in the middle attack. And yeah, so man in the middle attack means that we have someone who tries to get the information from the communication channel between Alice and Bob, and there are two different types of the attack. This person could passively eavesdrop the information from the channel. It's a passive type of MITM attack. And of course it can be active, meaning that the eavesdropper not only gets information, but also does something with that information, correct that, and send back to the communication channel, trying to confuse or spoil the information somehow. So it's called active MITM attack. Right. So in our particular example, we have Alice, right? We have Bob. They connected over this quantum communication channel, as well as classical channel. And for example, they use this BBA84 quantum cryptography protocol for communication. So what they do, right? They send the photons, or Alice sends photons to Bob for the key distribution. And what happens when eavesdropper appears in the system? So this person, and by the way, we call this person Eve. Eavesdropper, right? So what this person does? This person basically can put some sort of beam splitter to the system, like this beam splitter, and this beam splitter takes the photons and make them coming to the Eve, right? And and then Eve measures the photons and can send the photons back to Bob, and yeah, and spoil this communication channel, compromise this communication channel. And that would happen in the classical system, but in quantum system we send the information in form of photons, like photon by photon, and the information is encoded in the polarization of particular photon. And the problem is that Eve doesn't know the basis that Alice used to prepare each photon. So, and Alice, of course, doesn't reveal this information like before Bob receives the all bits, and before they check that nobody's if drops the information. So the best, I mean, not the best, what Eve can do, she can also choose the basis, and probably randomly, right? So she also chooses the basis, and in this basis she measures the photons that comes to her, and she of course gets some sequence of zeros and ones, but this information is meaningless because she doesn't know the polarization state of that Alice used. And and on top of that, if she tries to, like after the measurement, if she wants to prepare the photons and send them back, like sending them back to Bob, because of the no cloning quantum theorem, right? She cannot prepare the state before measurement. So she measures the photon. This process of measuring the photon collapses each particular photon in the different state. And she, of course, doesn't know the state of the photon before the measurement. And that's why she cannot clone the state. And the best she can do, just send these photons back to the channel, back to Bob. But in this case, when it happens, this is the main part of the story, is that, so for example, in this particular case, we had some photons that encoded the correct information. We denoted them by this 0, 1, 1, 0 bits. They were correct because the basis of Alice and basis of Bob were correct. But what if some of these bits were spoiled by the presence of Eve? In that case, when Alice and Bob compares the basis and compares the result of the measurement, right? Even though the selection of the basis would coincide, the polarization of the photon would be wrong. It would be spoiled by the presence of Eve. And when it happens, they would discard the transmission, the communication. Because if this happens, for the correct selection of the basis, they get wrong bit, then it means that this bit was spoiled by the presence of eavesdropper in the system. So let's write this down this way. So if Alice and Bob observe, see that some bits don't match, right? They discard the communication, because it is compromised. It was compromised. Yeah, so this is how this BB84 quantum cryptography algorithm, or the protocol works, and this is how it is protected against the presence of eavesdropper in the system. And so what's important here is that we basically need single photons. So we need to send the information in the form of single photons and the polarization of the single photons. We also need to be able to control the polarization of the photons at the Alice's side and the Bob's side. And this channel must be like synchronized. So we must be able to send the single photons at very well defined time instance, right? Like to synchronize this. For example, we cannot do that with like a light source, like a light bulb, because light bulb, well, it generates photons. I mean, a lot of photons, but we of course can dim the light source down to like very weak intensity, very weak power, so it will be irradiated by almost single photons. But the single photons will appear very randomly, just chaotically random. And we cannot predict when this photon will be emitted and will be absorbed. So we cannot synchronize the system. We have to have a very good light source that can be synchronized. Light source and light detector that could be synchronized. So we're gonna discuss this in more detail today. Do you have any questions regarding this quantum cryptography part?
No, Professor, it's clear.
Very good. Very well. So now let's change the gear and discuss maybe like very relevant or similar technology, which is not like developed because of some fundamental well, challenges of other types of qubits, but like for the completeness, let me bring this technology here. So this is the subchapter 4.5, and let's call this quantum money. Quantum money. Right. So so you know this problem of how it's called counterfeiting of money, of banknotes, right? And there are like many different approaches how to protect the banknotes from this counterfeiting problem. And today, like each banknote is like a very sophisticated how to say system, right? You've got very many different like ways to protect the banknote, and and of course these protection notes, pictures, emblems, logos, and etc., etc. They increase the intrinsic value of the banknote material fabrication. So the money become like more pricey, right? And people always try to find a way how to protect the money from being counterfeited. And in fact, at least theoretically, potentially, we can use the law of quantum mechanics, quantum physics to protect the money. And how this would work? Well, it would work in the way that very close to quantum cryptography that we just discussed. So let's suppose we have a banknote, right? Like a dollar from the future, and this dollar gets a number of qubit cells, like this, qubit cells, and each qubit cell can be polarized in different direction, right? For example, if this is a like magnetic spin, we can apply the magnetic field in, in different directions, and this way we polarize these qubit cells in a different orientation. And each banknote gets a serial number, right? It could be whatever, 32101235, something like this. And so the unique serial number, and according to each unique serial number, we encode this serial number into the polarization of the qubit cell. For example, something like this. Whatever. Yeah. So just distribution of polarizations of qubit cells. And yeah, so if we like imagine or that we have a good quantum bit like qubit, right, with a very long time, the coherence time, like a spin. If we would create such a qubit with a very long lifetime of the quantum state, we would be able to indeed encode this information, this serial number, into the number of the qubit cells, right? And like whenever you use this banknote, the bank can check the states of the qubit cells. So the bank can check the states of the qubit cells. Like, for example, if the bank or cashier, whatever, who receives this money, if they know that this, for example, this particular qubit is supposed to be polarized in the vertical direction, they can control that, and they can check that. But if you like try to measure these states of these qubits, you will necessarily spoil the states of the qubits. And again, because of this quantum non-cloning theorem, you cannot prepare the qubits in the same state. So after the measurement, the states are spoiled. They collapse to some particular state. You cannot prepare these qubits in the initial state, so you spoil the banknote. So let me write this down somehow. The qubit cell and confirm that the banknote is original. However, if someone measures the states. They change. They change the basis. They choose the basis randomly. They choose the basis randomly. If they don't know the serial number or like the way the banknote was encoded, the best they can do to choose to choose the basis randomly, and of course that spoil the code randomly and spoil the code, right? So this way the banknote is protected from counterfeiting. Yeah, pretty good. Of course, the main challenge here is that in contrast to like photons that we use for quantum communications in the optical fibers, and the photons can prevent, they can keep the coherence for a very, very long time. Some photons come to us from like very distant stars from other galaxies, and they keep the original polarization, so they can keep polarization for a very long time. In contrast, the qubits that would be useful for this technology, they must be based on other physical principles. For example, the solid state qubits or defect-based qubits or like quantum dots. Unfortunately, all those types of qubits, they keep the quantum coherence for much shorter times, like seconds in some particular solid state qubits, or even milliseconds or nanoseconds in other types of qubits. So so in reality, this technology doesn't work because of this problem of coherence. But yeah, as I said, I would present this here to show how we can use these principles of encoding of information into a quantum system for cryptography, for protection something, for quantum money, and etc. So this basically ends the part about quantum communications. I tried to keep it short, and for the rest of our course, we converging to the end of the course. By the way, we have just a couple of lectures, right? So towards to the end of the course, I would like to discuss the like main types of qubits. So let's start the chapter number 5. Call this main qubits. So, and my goal is to discuss the like very briefly again main types of qubits and how we work with them, right? Basically, how we can create the the superposition of different states in these qubits, and also how we can control the interaction of two qubits and creating the entangled states, right? And yeah, so this is the goal. And before going to discussion the different main qubits, let's ask ourselves what we need, right? What we expect from a good qubit for applications. So the answer to this question, of course, depends on the application area. For example, as we just saw for the quantum cryptography, we don't need much. It's enough to have just single photons, and it is very good that the photons don't interact because they don't spoil the quantum state, the polarization, and that's why basically we can use them. And also photons are very easy to generate them. We have a bunch of different lasers, and in some particular regimes of operation, these lasers can be used for quantum cryptography, quantum communications, and of course for quantum computing. For quantum computing, the requirements are more strict or more difficult to implement. So what we expect from qubits for computing? What we need? So first of all, we need a qubit, a system that preserves the quantum coherence for a very long time, as long as possible. So the system, the qubit, is supposed to preserve the quantum coherence for a very long time. For a very long time. So in the theory, this quantum coherence time is called T2 coherence time. And you might wonder why, where is T1? So T1 stands for the, energy decay, or the population decay time. And we will discuss that next time. But for the coherence, we call this T2 time. So the larger T2, the better. We need qubits with a very long quantum coherence times. I mean, by very long, I mean the time much longer than the typical operation time with the qubit. For example, for the photon, it would be time of propagation between Alice and Bob, and time of detection of the photon, something like that. For quantum gates, it will be the time of single gate and 2-qubit gate operations. These operations, they require some time, and the very long coherence time here means that the qubit preserves the quantum information for the time much longer than the typical time we need to proceed this information to operate with this information. So this is the property number one. The requirement number two, we need a qubit, we need system with good scalability. Scalability. What it means that if we need to build up a machine, quantum computer, we need like we want to be able to put many hundreds, thousands, maybe billions of qubits to the system, like the way we do with transistors and electronic computers. Modern electronic computers, they contain billions of transistors, and this is the result of this CMOS technology, right? And this is why our computers became so widespread, because of this CMOS and because of the scalability. So the scalability is very important. So number three, what we need, we need good control of quantum state, good control over the state. For example, in the case of a photon, we can easily control the state of a photon using these beam splitters, polarizers, etc. And unfortunately, like other types of qubits, they are not so easy to control. And in order to create this entanglement and superposition of different states, we need a qubit with good control. So then number four, what else we need? We need quantum entanglement, right? So for the computation, we must have quantum entanglement. In fact, this superposition effect, this is something that people knew for many years, since the discovery of light interference, right? People discovered that two waves, they can create a superposition of the two, and the superposition creates this interference as a result. So in fact, it was considered as a classical effect. So in the theory of waves, this is considered as a classical effect. Nothing very specific about the superposition, but the quantum entanglement is something that is considered truly quantum, and it enables not only quantum computing, but also sensing and quantum teleportation approaches, and some other algorithms of quantum cryptography. So it is truly quantum effect. And of course, we need this quantum entanglement for quantum computers for 2-qubit gate to 2-qubit gate operations. So there are several types of qubits, as I said. There are several types of qubits. And we probably discuss, if we have enough time, just 3 of them, like the most popular ones. And the main point here maybe to say is that there are no perfect qubit, no perfect qubit. So all qubits are different and they have pros and cons. Today we will discuss the photon, because we just discussed this cryptography, other area where we use the photons, so it's natural to go to the photons as a qubit in more detail. And of course, photons, they have pros, they have advantages, like they propagate at the speed of light, and they don't interact with other fields, so they keep the polarization for a very long time. But unfortunately, they don't interact with each other, so it's very hard to create the entanglement of 2 photons. That's why we don't have photonic quantum computers yet. And so they don't work that nice for quantum computing, but for the quantum communications, they are just perfectly good. So no perfect qubits, and the choice of the qubit depends on the area of application. Yeah, so let's proceed with discussion of different types of qubits, and we start with photonic qubits. So let me call this chapter 5.1 photonic qubits. By the way, do you have any questions by now?
No, Dr. Lex.
Okay. So photonic qubits, just briefly discuss the pros and cons and the main idea. So let's denote in green the advantages. So the first advantage is that photons have no charge. And since they have no charge, they are not affected by electric and magnetic fields. Right, and for this reason, they less. They less susceptible to environmental noise. They less susceptible to the to environmental noise. And this is very important. And this is for this reason the photons, they keep polarization state for a very long time. because the fields the fields don't spoil the polarization. I mean, at least weak fields. There are some areas of research where people study the effects of very intensive, very strong electromagnetic fields and how they affect light. You know that vacuum is not empty, right? It consists of the sea of virtual particles like electrons, positrons, and even though they are virtual, they burn for a very short time and then collapse. And if we apply a very strong field, we in fact can generate real particles from the vacuum. And these particles, of course, will affect the polarization of light, because the generation of real particles will make the light scatter from those particles and spoil the state. But for the weak fields, this is completely fair. So photons don't affected by the fields and less susceptible to environmental noise. And as a result, they have large coherence time. Large coherence time. This is the first very nice point, very nice advantage. The second advantage is the fact that they communicate, they propagate at the speed of light. At the speed of light, right? The largest velocity, largest speed in the nature, and this makes the communications very fast. So number 3, as I said, photons are pretty easy to generate, right? So we have a bunch of different lasers, light sources, like lamp bulbs, etc. And yeah, we can generate how to say, countless number of them. In this sense, this particular type of qubits is very scalable, right? So very scalable, very scalable. Right? We can generate many qubits very easy. And finally, particularly important for computing, the photons, they are very it's very easy to realize single qubit operations. Single qubit operations are very easy to realize, implement. Unfortunately, as I said, photons have disadvantages, and well, some of them make it make it really difficult to realize a quantum computer. Some of them are not so difficult to get around, and one of these that we discuss, the need for single photon sources. Single photon sources, SPS. Single photon sources, and let's return for a second to this quantum cryptography channel, right? So as we just said, in order to implement this quantum cryptography, we need photons that are emitted in in a very predictable way, right? We need to generate the operation of like the Alice sending the photons and Bob receiving the photons, and they have to make sure that they generate and measure the same photon, the same particular photon. And if they are distantly located, Alice and Bob can locate in the different countries, or Alice can be on Earth and Bob can be on the moon. They have to be sure that they emit and detect the same photon. And also, of course, the channel is not perfect, and it's possible that some of the photons, they escape from the channel or get absorbed or scatter. I mean, something happens to the photon, and Bob needs to know that, like, if he doesn't receive a photon, it means the photon is lost, and they just discard these lost photons from the communication channel. So the light source must be very predictable, and the light source must emit photons one by one in a predictable way, and this is the need for single photon sources. And at this moment, we need to discuss what actually makes what's the difference between the light source, like light bulb. Let's call this light bulb, versus laser. So what was the difference between light bulb and laser? And on top of that, what's the difference between laser and light bulb versus single photon source? What makes single photon source a unique type of light source? So let's consider some generic light source, right? So before building the quantum theory, we assume that, or we describe this light emitted by light source as a wave propagating in space, and this light, this field, would be described by like harmonic function like this. If you assume this light source emits just one single frequency, it would be, in the perfect case, it would be something like this, cosine omega t. Right, so this is simple, perfect case of monochromatic light. Monochromatic light. in reality, of course, we have this phase fluctuating, and the amplitude of this field also fluctuates. Let me write this like this. So it would be another function of time with the amplitude that is a function of time, and cosine would be omega t plus some phase would be also function of time. And in reality, of course, this amplitude function of time and the phase function of time would be random. Right, it would be some sort of like noise in the system. The phase can fluctuate, and the amplitude can fluctuate, and this causes the need of predicting the field. And in order to describe the predictability of the light source, we introduce this function called field autocorrelation. Let me write this down. So the prediction of the field is characterized by the parameter field autocorrelation. Or autocorrelation function, unless denoted by gamma. So how we introduce this autocorrelation function? So basically, suppose we know the value of the field in some time moment t, right? And we compare this field value with the same, but in another time moment. Basically, we shift the time moment by the tau, and we compare the value of the field. And for example, if I have the random function of like the field function of time like this, right? And then suppose I have shifted this field and time by tau. Let me maybe put it here. Right. So this tau would be like this. So small tau. So we see that if we take the integral of this field E of t times the E of t shifted by this tau. And if I integrate over all the time, right, what I would get? I would, if this tau is small enough, first of all, if tau is 0, this will be integral of t times, this will be integral of e times e complex conjugated, which is the intensity by amplitude, by definition. Sorry. And if this tau is small enough, we see that the field is like self-correlated because it didn't change much to lose this correlation between the field in the time moment t and time moment t plus tau. But if this time moment is large enough, the correlation, the self-correlation, optical correlation of the field is washed away, and the correlation function is 0. Right. So in order to describe all this, we introduce this autocorrelation function, which is of course the function of theta, or sorry, tau, and this is simply the integral of t times e complex conjugated t plus tau dt. And to make it shorter, the notations we write this as a averaging over time in this brackets e complex conjugated tau. This way. And as I said, if tau is 0, then I get intensity, and I want to make my autocorrelation function is dimensionless, and to normalize it to 1. So I divide this quantity by intensity. In result, I get the the correlation function. This is the first order correlation function. So it's called first order correlation function. We denote it by G. And the formula, the definition is this one, T plus tau, average over time. And here the average of intensity. So this is pretty important quantity, important formula, right? And it describes the G1. It describes the coherence of the field, and the word field here is important. So it's a function that describes the coherence of field, and based on this analysis, let's draw schematically how it depends on the tau. So it's G1 of tau depending on tau. It starts from 1 because when tau is 0, I get intensity over intensity, so it's 1, and then it of course decays like this, and when it decays by a factor of, well, 1/2, I can say that my system almost lost the coherence, and this time of losing the coherence is called coherence time. Coherence time. So the coherence time defines the, 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 the characteristic time when light source, or the field loses the coherence, it means that after this time, the time larger than coherence time, we cannot predict the field after this time. We cannot predict the field. Let's write this down like this. So if my tau is around 0, my first order correlation function is 1, and this means the field is predictable in the next moment of time. However, if the tau is larger than the coherence time, the correlation function is around 0, which means that we cannot predict the field in the next moment of time. And also, important point about this correlation function is that, or better to say, this coherence time, is that it defines the light source bandwidth. So it's known from the Fourier transform analysis, and also originates from the quantum uncertainty principle, is that the bandwidth of the light source times this coherence time is around 1. And this means that the bandwidth is something like 1 over coherence time. So if a light source has a small bandwidth, that means that the coherence time is large, and vice versa. If the coherence time, let's say, very small, then the bandwidth will be very large. Okay.
I have a question here. Okay, Alex.
Yeah. Yes.
It's related to the quality factor as well. So we have also learned that the bandwidth is also, I think, inversely proportional to the quality factor. So is it also related to this coherence time? Means, are these two terms as well related?
Yeah, exactly. So I will probably discuss quality factor later on, but yeah, so the the bandwidth basically is inversely proportional to the quality factor, and the coherence time is proportional to the quality factor. But there are some points here that we can discuss maybe later. Because like traditionally usually by quality factor we mean that like like how fast the energy decays in the system. For example, if quality factor is, let's say, 100, then the field oscillates around 100 times before it decays by a factor of E. This coherence time is not about energy, it's more about the field, right? How we compare the fields. So it describes the autocorrelation of the field rather than the field energy. So I would say that the two are related, they connected, but not exactly the same.
Okay.
Yeah, but yeah, thank you for thanks for the question. Do you have any other, by the way?
No, answer.
Oh, okay. So yeah, just let's compare maybe the spectrum of a light bulb. So for the light bulb, the intensity would be something like this. This intensity bulb, right? And so as I said, the coherence time of a light bulb source is very small. It can be pico or even femtoseconds, so it's a very short time. And but in contrast, the light source spectrum would be something like this, very narrow line, and so this laser, and that's because the coherence time is long. The coherence time is large. I mean, not much larger, let's say, much larger than the light source of than the light bulb. And also, let me maybe emphasize here that when we describe this first order correlation function, we assume that intensity is constant. So here we assume that intensity, which is time averaged model absolute value squared of the field, is constant. Well, it is not necessarily constant. For example, if you look at this definition of the correlation function, first order correlation function, we see that intensity stands in the denominator, right? And the numerator is also like time dependent. What's important here is that the fluctuation of intensity don't affect the first order correlation function, and we need to introduce another characteristics that would describe the correlation or coherence properties, correlation of the intensity. And in order to describe the characteristics of light source intensity fluctuations, we need to bring this second order correlation function. So it's called G2 correlation function. So it's a second order correlation function. Second order correlation function, and it describes the correlation of intensity. Again, the word intensity here is important. In contrast to the correlation, the first order correlation function that describes the coherence of field, in this case of the second order correlation function, we deal with the intensity rather than field. And in fact, when we have a general light source, we can measure this intensity in time using some sort of optical sensor, detector, and of course the light intensity would be like time depending function of time, right? So some fluctuations. And this is something that is not described by first order correlation function. And why it's important? Well, it's important because, as I said, the intensity is nothing but the absolute value squared of the electric field. This is what we know from the classical physics. And also by definition, intensity is nothing but the power per unit time per unit area, right? So basically this is just energy that our light source carries per unit time, per unit area. But from the quantum point of view, intensity is nothing but the number of photons times the energy of a single photon. So if you know the number of photons that is generated by your light source, you just multiply this number of photons by energy of single photon, you get intensity. You get intensity. And since photon for the fixed frequency is nothing but the number of photons, or the intensity is nothing but the number of photons, it means that if we measure the light intensity to be fluctuating, it means that it is actually the fluctuation of photon number fluctuations. And so that's why these characteristics, this G2 characteristics is so important when we talk about single photon sources, because single photon sources are described by second order correlation function. So second order correlation function, that's what we need to characterize single photon sources. Any paper you read about single photon sources, they discuss second order correlation function. This is something you must know when we talk about photonic qubits, quantum optics, photonics, etc. So second order correlation function. And let me bring it here. So in a similar way, as we introduce this first order correlation function as the product of fields and finding the mean value by averaging over time, right? Second order correlation function is defined the same way, but like replacing the fields by intensity. So in this case, I write this second order correlation function this way. So it's a mean value of the product of intensities. So well, intensity is real value, real function, right? So no need to put the complex conjugation here. And of course, we normalize to the product of two mean value intensities. Second order correlation function. Let's discuss how we define the second order correlation function in experiments. And from this example, it will be much clearer what's so important about this. So the experiments that we're gonna describe, and this is like one of the most important concepts in quantum optics. It is called HBT experiment. where HBT stands for these two names, this Hanbury, oops, Hanbury Brown. So Hanbury Brown is the name of one person, one scientist, and Twiss is another person. Hanbury Brown Twiss. Hanbury Brown Twiss experiment. So in this experiment, instead of measuring the field interference, we measure the interference of light or light intensity. So suppose we have a light source, right? This light source emits photons. These photons, in form of a light beam, come to the beam splitter. So this is beam splitter. And of course, one part of these photons go through and another one, 50%, bounce off, then reflects from the mirror and directs to like another way here. And one beam goes towards one detector, and the second beam goes to another detector. So it's just a photon counter that can detect one single photons. And then these single photons, they create the currents in these detectors, and then we can compare the currents like electronically. So it's just a computer counter system to compare the currents. And what else? And what else? We can also introduce some sort of a delay system, for example, here, that would bring this tau to the experiment. And this is light source. Light source. Hanbury Brown Twiss experiment. Let me make a little break and I will be right back in 5 minutes. I'm back. Where I was. Yeah, Hanbury Brown Twiss experiment. So first of all, let's describe this G2 correlation function, second order correlation function, when tau is very large. So very large time shift between two detectors. So in this case, our averaging of the product of two intensities turns into the product of two averages of the intensity. So it will be the mean value of the intensity and times mean value of the intensity after this tau, right? And and divided by basically the same in the denominator. So the second order correlation function for very large tau would be 1. And this 1 means that the intensities are not correlated, are not correlated. And in other words, all the photons that come to the first or the second detector, they are uncorrelated. So in contrast to first order correlation function, where uncorrelated fields mean that the function is equal to 0, right? The vanishing correlation means vanishing first order correlation function. In terms of second order correlation function, uncorrelated photons mean that second order correlation function is equal to 1. And now let's consider a particularly important case of the time delay of 0. So no time delay between first and second detector. And in this case, if I have no, if my tau is 0, then this intensity in the time moment t times basically the same, so I get square, right? So it will be mean value, mean the average of intensity squared. Oh, sorry, the average of intensity squared over the square of average of intensity. The average of intensity squared over square of average of intensity. Something like this. Yeah, and yeah, let's particularly emphasize that tau is 0. Tau is 0. And let's also emphasize that if intensity is weak enough, then second order correlation function at the moment at the tau 0 describes the statistics, describes statistics of a particular single photon. By this I mean that in contrast to the case when tau is very large, we deal with different photons in the system. But when tau is vanishing, when tau is 0, we have no delay, and that means that we deal with the same photon or like a group of photons, as we will see in a minute. And this is what makes this correlation function particularly important. It describes the single photon itself rather than the statistics of different photons in the system. And there are 3 cases here. The three cases possible. First one, when this mean value of intensity squared is larger than the square of intensity, right? So in this case, the second order correlation function at the moment 0 is is larger than 1, and of course this means that it is larger than the same function when tau is infinitely large or very large. Let's put this infinity here. Right. So as we said, when second order correlation function for the tau is when the tau is very large, it goes to 1. So this is like asymptote of this function. It's 1. So that's why I compare this function with 1 here, because 1 means that the photons are not correlated. And so in this case, the second order correlation function is larger than 1. And this means that the photons are correlated. And we call this case classical light. Classical light. Or, well, correlated light. But so it's here the correlation is not in terms of field, but in terms of photons. So it's saying that this is correlated light means that means something about the statistics of the photons emitted by this light source. So you will understand in a second what that means, what I mean by that. So this is the correlated light. Correlated light. So so if I draw schematically the sequence of photons that come to the detectors, I mean, the intensity is proportional to the number of photons. And the fact that second order correlation function is larger than 1, it means that my system receives more than, in average, it receives more than 1 photon. At the same time, this is the second order correlation function without time delay. So it means that more than 1 photon, I mean the each pulse, like each each photon comes to the system not as a separate or single photon. It comes to the system as a group of photons. This is like pretty important point to understand. Let me schematically draw this way. So I draw it like groups of several photons in the system. It can be 1 photon, it can be more than 1 photon, it can be 2, it can be 3, it can be 4. The point here is that the number of photons in each pulse, let's call this pulse or so, in each group is random. So this number of photons here is random. And also, so this is random. And also the time delay between subsequent groups of photons is also random. So and this effect of photons when they like make a group, it's called bunching. 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 So yeah, so now having introduced this word, it might be better to discuss this. So yeah, in terms of classical light, and by the way, classic light means, for example, light bulb. Light bulb. Like light that we have like from any incoherent light sources, light bulb from the sun, from the TV, from I mean whatever. There are a lot of examples here. So all these light sources, they called classic, and another word is chaotic light. Chaotic light. And I mean, at first it can sound a little bit confusing, but in this case, in the case of second order correlation function, chaotic means correlated. Because correlation here means bunching, when photons prefer to make bunches of or groups of photons. And so a light source, for example, if the light source is like big enough, it's not a single atom, it's like a light bulb with billions of atoms there. These atoms emit light, and because of there are many atoms there, they emit multiple photons, and multiple photons, they bunch into groups of photons, and each group may contain different number of single photons. It can be 3, 2, 1, 4, it can be 10, and in this sense, these groups of photons, they are not predictable, because you cannot predict how many photons will be in the group. You can't predict when the next group of photons will be emitted. You cannot predict like anything about this light source. This makes this light source chaotic, and yeah, and this is the classical light source. So in the case of the Henbury-Brown-Twiss experiment, let me schematically draw this way. So we have one detector, second detector, right, and the photons can arrive like a bunch of 3 photons here, but for example 2 photons here. It can arrive like 1 photon here, but like 4 photons here. So that's why the correlation function is larger than 1, and also That's why this light source is chaotic. This is the first example of light source. The second example, or the second case, is so-called coherent classic light. Coherent. Coherent classic light source. So in this case, as you probably already get, so in this case, the mean value of intensity squared is equal to square of mean value of intensity. So it's something like this. Right. So since these two are equal, it makes the correlation function at the moment, at the time shift 0 to be equal to 1. And it is exactly equal to the case when we make tau to be infinitely large, right? So this is not correlated. Light source. No correlated light source. What it means? It means that if you, for example, consider if you, for example, consider a dim light source that emits like almost photon by photon, we would get something like this. It would be a sequence of photons, but the time, like distance between each between the neighboring photons would be unpredictable. So it's still chaotic, but times are random. Well, it doesn't mean that the coherent light source is only single photon source. It can also emit the groups of photons, and for example, in this Henbury-Brown-Twiss experiment, it would look like, again, two detectors, single and second, or the first and second, and these detectors can detect single photons, it can detect more than one photons. The point is that these groups are now correlated. So if my first detector receives one photon, the second also receives one photon. But if I have a group of 3, then the first detector receives the group of 3 and the second receives the group of 3, so that the ratio of the two of these two values gives me 1. So this coherent light source can emit photons like one by one if the light source is weak enough, but the time sequence, right, of this emission is not predictable. So this is actually the case of laser. So this is how the laser emits light. Laser. So any laser, like the one we have in the lab, emits photons like this. And the second order correlation function of a laser is equal to 1. And for quantum communication, this already, like, for some of these protocols, for example, I mean, there are some protocols that would be okay with the light source. Excuse me. Yeah, for some protocols of quantum cryptography, light source like this would be okay, but still, the fact that this time sequence of the repetition time of the photons is not predictable. It's very hard to synchronize the Alice and Bob sides, so still is not a good source of light for quantum communications, and definitely not good for quantum computing. And finally, let's describe the third type of light source, and it's called non-classic light. Non-classic. Non-classic light source. And in this case, the mean value of intensity squared is less than square of intensity. So this is already like something unusual. And this makes the second order correlation function less than 1. And in other words, this means that second order correlation function is less than second order correlation function of uncorrelated photons. So it's in other words, this is something like anti-correlation. When a photon anti-correlates with other photons and with itself. And this is very, very interesting and very like non-classical. In terms of Hanbury, Brown, and Twiss experiment, it would look like something like this. So I again have 2 detectors, and let's suppose I have a source like this with second order correlation function less than 1. And suppose I have a photon that comes to or like goes towards the first detector. And the presence of the photon in the first channel makes like anti-correlation in the second channel. I denoted by this open area. So this is my photon, and the presence of the photon in the first channel anti-correlates with itself in the second channel. This is very interesting, and vice versa. The presence of photons in the second, like, anti-correlate with itself in the first one. Very interesting and very unusual, but the point is that only this type of quantum sources allows us to emit photons one by one and with well defined repetition time. So this time between the two photons well defined now. So, and this is the case of single photon source. So the single photon source, a good single photon source, emits photons one by one with a very well defined repetition time. And in the quantum picture, it corresponds to anti-bunching. So let's write this word down here. Anti-bunching. Anti-bunching. So in contrast to bunching, when photons like try to group in the groups of like a number of photons, in the case of anti-bunching, they try to like effectively repulse themselves and stay like away from other photons. And that's why this word anti-bunching. Very interesting. Yeah, and let's draw schematically how this second order correlation function behaves if I increase the tau from 0. So when tau is 0, the correlation function is is 1, right here. And for the coherent classic light source, like a laser, I have constant 1. So this is laser. In contrast, the chaotic light source, it starts from the larger value and also decays to 1 as tau grows. So this is chaotic light source, like a light bulb. The photons come in groups or bunches of groups or bunches of photons, and the number of photons in each group is chaotic, and the time sequence is random, so it's completely a random process. And finally, the quantum light source, it starts from below 1 and also grows to 1 like this. So this is quantum light source with this effect of anti-bunching effect. Yeah, so as a conclusion of this section, let me just repeat that we need quantum unbunched light source for photonic qubits, because only in this way we can predict when the photons appear in the system. We can synchronize the source and the receiver, and we can distinguish one photon from another photon, which is also important. So let me write this down like this. So the single photon sources are sources of anti-bunched quantum light. Quantum light means photon by photon. And what is also important is that in the case of single photon sources, the single photons are emitted in response to single trigger pulses, to single trigger pulses. That means that if I want a photon, I excite, like I send a pulse, trigger pulse. It can be like a pulse of current. And it generates a single photon. And if I need another photon, I apply my trigger pulse and generate another photon in a very predictable way and at my will. Yeah. So this is about the correlations and the coherence of photons and what makes the difference between light source, laser, and single photon sources, why we need single photon sources for quantum computing and for other quantum applications. And then finally, let me just bring to, for the completeness, let me also say that photons, and I denoted in blue, right? So this is the disadvantage of photons. So the point of entanglement or better say, like, it's difficult to achieve entanglement in the photonic system. And that comes from the fact that photons don't interact in free space or in the vast majority of transparent materials. Like glass, for example, or like silicon dioxide, for example. These materials are linear, and the photons in linear systems don't interact, and that's why it's very hard to achieve interaction between the photons, and so no quantum entanglement between photons in these systems. So we need medium with strong nonlinearity. Strong nonlinearity to enable quantum entanglement, to enable entanglement. And not only strong nonlinearity, but also this material, this medium must be large enough, because the photon propagates very fast. That's right, but if you need some time to to achieve strong interaction between photons, they have to pass this material, or they have to be in this material for a sufficient time, and that makes the system large enough or big enough to enable these processes. So this makes the photonic quantum systems large. That's okay for quantum cryptography, because quantum cryptography is a very extended system. You have one transmitter, one receiver, the distance would be huge. But for the computers, like quantum computers, this is very challenging to make photonic quantum computer because of these problems, because of these issues. And for the same reason, like it's very difficult to achieve 2 qubits, 2 qubit gates. So 2 qubit gates and interactions are very challenging. And finally, let me just mention that so a photon interacts strongly with materials, right? Some materials, and if you need like if you want to interact with a particular photon, we need to, I mean, especially in the case of quantum computer, we need somehow to trap the photon. And to do so, we use these resonators, right? So we need lights. We need light storage. Hence, the need for resonators with high quality factors or large Q factors. Large Q factors. So these systems are called quantum memories. In the case of quantum, like photonic quantum computer, we need a resonator to enable this quantum memory effect. So we trap a photon there and keep it for a while before we like do something with the photon, read out it, etc. So this is like another challenge to the systems like that, based on photons. So next time we're gonna discuss other types of qubits. I really hope that I will have enough time to cover what I initially planned for this course. Very good. So let me stop the recording and then we can discuss the formal things.